Hello everyone, welcome back to my YouTube channel. So today we are going to continue a chapter that is work and energy. So this is part 3 of the chapter. If you want to watch part 1 and a part 2, the link is in description to watch it. Now in the previous part, we have discussed about work and it's time to discuss about energy. So today we'll be starting our session discussing about energy. So there are different forms of energy on Earth. The sun is considered as the elemental form of energy on the Earth. In physics, energy is considered as quantitative property that can be transferred from one object to perform work. So, to perform any work, we require energy. And in physics, we consider that energy can be transferred from one object to another object. Hence, we can define energy as strength to do any kind of physical activity. Thus, in simple words, we can define energy as the capacity of body to perform work is called its energy. Let us discuss now the forms of energy. So there are many different forms of energy. Some of them I have mentioned here, like electrical energy, thermal energy, light energy, solar energy, wind energy, nuclear energy, tidal energy, sound energy, chemical energy, biomass energy, wave energy, mechanical energy, geothermal energy, and heat energy. So these are different forms of energy and there are many more forms of energy. Now these energy can be converted from one form to another form. And this we will be learning in the concept called transformation of energy. Now we will discuss about the units of energy. The units of work and energy are the same. The international system of units of measurement of energy is joule. We have seen that the SI unit of work is also joule. And similarly, the SI unit of energy is also joule. So units of work and energy are same. Joule is derived a unit equal to energy expended in applying a force of 1 Newton through a distance of 1 meter. So the definition of joule says that it is a unit equal to how much energy we have spent on applying a force of 1 Newton through a distance of 1 meter. And that energy we have spent is referred as 1 joule. However, energy is also expressed in many other units not part of the SI system, such as ergs, calories, kilowatt hours, kilocalories, etc., which require conversion factor when expressed in SI units. Explain relationship between the commercial and SI unit of energy. So the SI unit of energy is joule and the commercial unit of energy is kilowatt hour. So between joule and kilowatt hour, what is the relation that we have to explain? So first of all, I will write here commercial unit of energy. That is equal to kilowatt hour. So this is our commercial unit of energy. And the SI unit of energy is joule. Okay. Now we have to explain the relationship between both these units. So first I will take kilowatt hour. Since this is not a SI unit, I will have to convert this unit into SI system. 1 kilowatt hour. This is kilo, K for kilo, W for watt, and HR for hour. This is equal to 1 kilowatt hour. This has two terms. One is kilowatt and another term is hour. So I will split this into 1 kilowatt into 1 hour. Okay. Now, kilo means how much? Kilo means 1000. So 1 kilo I can write 1000. 1000 watt into 1 hour. Now 1 hour. Now the SI unit of time is seconds. Now I need to convert this hour into seconds. So how I'll convert? First we'll convert hour into minutes. We'll multiply it by 60. So 1 hour is equal to 60 minutes. Now you have to convert minute into seconds. 1 minute is 60 seconds. So how 60 minutes will be equal to 60 into 60 seconds. Again, we have to multiply by 60. So you are going to get 3600 seconds. So 1 hour is equal to 3600 seconds. Now 1000 into 3600 will give you 36 lakhs. Watt into second is nothing but equal to 1 joule. So we'll write in place of watt into second, we'll write joule, and 1000 into 3600 is 36 lakhs. Now we'll just shift the decimal places. I can write 36, and these are 1, 2, 3, 4, 5 zeros. So 10 raised to 5 joule. Or you can write 3.6, again shifting one decimal place, 10 raised to 6 joule. So 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joules. Let us move to the next topic, that is kinetic energy. Kinetic energy is a fundamental concept in physics that describes the energy transferred to an object due to its motion. So any energy which is transferred to an object due to its motion, that energy is referred to as kinetic energy. In order to accelerate an object, force must be applied, which involves performing work. If you want to move one object, if you want to accelerate one object, you require force which is to be applied on that object. And on application of force, work will be done. So that energy which will be required to do the work, that energy will be referred as kinetic energy, as the object is accelerating, object is moving. When work is done on an object, energy is transferred, resulting in object moving with a new speed. This transfer energy is known as kinetic energy, and it is determined by object's mass and speed it achieves. So kinetic energy is determined with two things. First is the mass of the object and the new speed which is achieved by the object. So we can define kinetic energy as the energy which an object has because of its motion is called its kinetic energy. Let us see some examples. First is water which is flowing. Next, you are walking, throwing a ball, aeroplane flying, cycling. Now you can see in these all examples, there is motion in the object. Expression for kinetic energy. Now we are going to derive expression for kinetic energy. There is a formula for kinetic energy. As I said, kinetic energy depends on two things. One is mass of the object and velocity of the object. So we are going to derive the relationship expression for finding kinetic energy. So here first we'll be writing the description. So we'll write the first point as consider an stationary object. Consider a stationary object of mass m with initial velocity u, which is equal to 0. Second point we'll write, we are applying a force to move the object. So on application of force F, on application of force F, capital F, the body moves with acceleration, or the body accelerates. The body accelerates, accelerates. The body accelerates with acceleration A. Third point we'll write, after time interval t, the velocity of the body is v. After time interval t, the velocity of the body is v. So this is our description of the body. First, we have mentioned, we have considered a stationary body of mass m. Initial velocity is u, that is 0, because it is a stationary object. When we applied a force F, the body accelerated with acceleration A. And after some time interval T, the velocity of the body is V. So after some time, the body will stop and it will cover a certain distance. So we'll write the displacement during this time interval is S. The fourth point is the displacement during this time is S. Okay. So this is our description. Now after writing the description, now we'll move on to the main part of the our expression. So here, first we'll start with work. We have applied force. We have done certain work. So work done on the object. What is work done on the object? Work done on the object is. We know that work done is nothing but equal to force into displacement. So this is our equation number 1, right? Now we have to replace this force with some another term and displacement with another term. Okay. Now how we'll replace force? So we have learned that by Newton's second law of motion, by Newton's second law of motion, force is nothing but mass into acceleration. This will be our equation number 2. And we have to also replace the displacement with some another factors. So that also we have learned in chapter number 1. By Newton's second equation of motion, what was the second equation of motion? S is equal to ut plus half at square. So that we are going to use. So therefore, S is equal to ut plus half at square. Now, if you substitute here, the value of u is 0. So this term will, the whole term ut will be equal to 0. So S will be equal to half at square. This is our equation number 3. Now, from all these 3 equations, from equation 1, 2, and 3, what we can write? Work done is equal to, in place of force, we'll write mass into acceleration. In place of displacement, we'll write half at square. So work done is ma into half at square, right? So finally, we can write, therefore, work done is equal to m half into m into at the whole square. As you can see, there is t square is there and also a is 2 times. A into a will be a square. So I'm writing at the whole square. So this will be my equation number 4. As I said, in kinetic energy, there are 2 things. One is mass, another is velocity. Now here, I have got the term mass. Term of mass is there, but I want the term of velocity. So I need to do some substitutions here. So again, I'm going to use here equation of motion using Newton's first equation of motion. What was the first equation of motion? V is equal to u plus at. So V is equal to u is 0, V is equal to at, right? Now we have to substitute V is equal to 8 in equation number 4. So substituting V is equal to 80 in equation number 4. So we are going to get work done is equal to half into m into, in place of 80, we will write V, so it will be V square. So finally, we are going to get work done is equal to half mv square. Now what is energy? Energy is capacity to do work. Energy and work are equivalent to each other. So I can write kinetic energy which is gained by object is nothing but the amount of work done by the object. The energy required for the object to do the work, that is kinetic energy. So the whole amount of energy that is gained, kinetic energy which is gained by the object, is nothing but the work done by the object. So here, work done and kinetic energy are equivalent. So we can write the kinetic energy gained by the object is the amount of work done on the object. Therefore, we can write kinetic energy is equivalent to work done. So we can write kinetic energy is nothing but half mv square. So this is a formula to find the kinetic energy, that is half into mass into velocity square. I hope you understood how we have derived the expression for kinetic energy. If an object has zero momentum, does it have any kinetic energy? So this is the question we have to explain. Now, if you remember, we have discussed in chapter number 1, what is momentum? What is momentum? It is a product of mass and velocity of the object that we denoted by P, that is product of mass and velocity, mv. Okay. Now, from they have told that object has zero momentum. That means P is equal to 0. That means mv is equal to 0. From this, we can see that v is equal to 0. Since mass of an object is never 0, there will be any number for mass. But if velocity is 0, then the answer will be equal to 0. So from this, it implies that velocity of the object is 0. That's why the momentum is 0. Now we have derived the expression for kinetic energy. Kinetic energy is equal to half into mv square. So half into mv square. V is equal to 0. So kinetic energy is also going to be 0. They have asked if an object has zero moment, does it have kinetic energy? So no, it doesn't have kinetic energy. So this is the end of today's session. Today we learned about energy, kinetic energy, forms of energy, and the expression for kinetic energy. So I hope you understood and found this video interesting. Do like, share, and subscribe our channel. Thank you.